Good afternoon. This is Brett Towler with the U.S. Fish and Wildlife Service. I want to thank everyone for giving me the opportunity to speak to you about our turbine blade strike analysis model. This is a desktop tool for estimating the mortality of fish and train through hydroelectric turbines, and I hope you'll find this useful. Those of you that have worked with hydropower for some time know that there's an interest in reducing the mortality of fish that are entrained through hydroelectric turbines. So often this is done with field studies, balloon tag studies, and so forth. But quite frequently it's done with a desktop analysis. And historically those desktop analyses are usually performed by the industry's consultants. And they're based on some well-known methods. One of the more popular methods is the Franke method. There are a variety of other ones. Our motivation in putting this model together was to simply, for lack of a better way of saying it, democratize that tool and provide it to both the service biologists and other partners that want to perform these kinds of desktop studies in-house. We started working on this back in, I think it was about September of last year. Both Jessica and I have had some experience programming, so decided to see if we could turn what was a Excel-based analysis into something that was a bit more user-friendly. In other words, slap a global user interface front end on the calculations. And so this was all coded in Visual Basic for Applications, which is, if you're not familiar with it, is a pretty high and user-friendly programming language that's actually embedded in Microsoft Excel. Now the upside of that is, of course, that anybody can use it. That is, anybody with Office, which is certainly, like I said, democratizes the whole thing because most of us have Office. It doesn't require any special software. So the methods in the model, or TBSA as we abbreviated it, are based on this paper that you see up on the screen. This is done by Gary Frank back in 1997 and a variety of other co-authors. It's often referred to as the Franke method. You can see the equations, and I certainly don't expect you to make those out. But essentially what they do is relate some of the well-known geometry of turbines, that is the inlet diameter, the outlet diameter, the number of blades, the type of turbine, the RPM of the turbine, to the probability that a fish of a given length moving through that turbine is going to be struck. And this is the foundation for a lot of those desktop analyses that I mentioned. So these are the equations that are all bundled into that Excel model that I mentioned. So the model is set up, and when you open it up, and we'll go through an example here in a bit, when you open it up it's going to look very much like any other Excel file with a lot of information on it, and everything is kind of confined into three tabs. Tabs are sheets that you can pick out at the lower bottom left of any Excel file. That is the Methods tab, where all the references for the methods used are detailed. It's static, it doesn't change, there's no user interface to that. There's the Root Data tab, and that's where you put in almost all of your inputs. The geometry I mentioned about the turbine and other project information, like is there a spillway, is there a bypass, what's the probability that fish will move through the different routes. And finally, the third tab is, once that information is added into the Root Data tab, the user would then open up the Simulation tab and run the model. So here again, a lot of details. This is actually what's on that method sheet. And again, I don't expect you to see that, but just to impress upon you that there's quite a bit of information in there. Certainly a description of how to run the model, the background equations, some information on how the fish populations are statistically modeled when you run a simulation, as well as what I think is a pretty complete glossary of terms. So again, that's just a reference, and once you get comfortable with the model, you certainly don't need to spend too much time on this sheet. The root data tab looks like this, and you can see the headings up at the top moving from left to right. There is the root name, the root selection probability. That's where you might enter what the probability that fish would go through each of these routes, and in the absence of better information, that's typically based on the amount of water. The third column over there is built by the model itself and just is the cumulative probability for each one of those routes. The next column is something internal that tracks the calculations or the calculation type. The next 10 columns or so, 11 columns, really contain all the data that you want to enter. What's highlighted in the red box there is all the turbine information, so that gives you an idea of the kind of information you would need to run a model like this. Now, this is something that the hydro companies would certainly have available to you if you requested it, or you might be able to pull it out of an existing report or study that was done during licensing. As a general rule of thumb, anything you find in the model that is in blue text is something you can change. The rest of it's protected, so you know, knock on wood, hopefully people don't find a way to break it. Sooner or later somebody will, but for the most part, if you try to alter some of these other columns, it'll give you a warning saying that you can't. So again, the blue font indicates a user input. The next slide shows the lambda coefficient, and I pulled this out because I'd like everybody to pay special attention to this. When the model was developed, that is when Frankie did this initial work, they calculated a theoretical probability of blade strike based on essentially the physics of that blade moving around, but they had to calibrate it or correlate it to known observations of fish kills. So the lambda coefficient is basically stepping down what the probability is of actual strike to, of the theoretical strike to actual strike. The thing to remember is that the higher the lambda, the more likely it is that you are going to kill the fish. The lower the lambda, more likely that the fish will get through safely. As a general rule, I would recommend using 0.2 for lambda, and I think Frankie backs that up in his paper, but you can play with that a little bit. I point it out now just because it is a parameter that gets played with a lot when you have to read a third party's analysis, and I encourage you to pay attention to what lambda they used, and if they use something other than 0.2, I suggest you ask them to validate why they use that. So actually running a simulation, when you open up that third tab, the simulation tab, this is what you'll see. You'll see a header at the top, a table, a big run button, a couple of other buttons that I'll go through with the example. And the first thing you need to do, remember that I mentioned that the blue text was for user input. You'll need to tell it some information about the fish population that you're going to run through this simulation. So in this case, what I've given it is 1,000 fish will go through the powerhouse. They have a mean length of 18 inches, so this is an adult shad with a standard deviation in that length of 3 inches. Once you enter that, you can run the model, and you click that big run button. And what you will see is the table below gets populated with the results. Now on the screen here you only see 22 rows down to row 32, but 22 individual fish results. I can't show it obviously here, but there would actually be 1,000 different results if you were to pan down the page, but it gives you a sampling of the information you're going to get. So moving left to right across the screen, the first 3 columns summarize the individual fish information. It puts an ID on the fish. It tells you what the length of that fish was, and I should point out that since you've told it there's 1,000 fish with an 18-inch mean length and a standard deviation of 3 inches, it uses a normal distribution to determine each individual fish's length. It converts that then to feet, which is an input into the model. The next 4 columns or so is the route selection. So based on random probability and the distribution that you gave it in the route data tab, it tells you where that fish is going to go. And you can see in column G how that is called out as downstream fishway, unit 2, which was a Kaplan. 1 went over the spillway. I think that's the 5th fish. And you'll see a sampling as that changes as it goes down. Moving over to the next 5 columns or so, those are the strike calculations. So based on the description of the geometry of that unit that you gave it in the route data tab, excuse me, it will calculate what that probability is. And notice again in that column L, paying attention to that lambda value, because the results are highly dependent upon it. Finally, the last 4 columns tells you whether or not the fish survives. So again, based on a random number generated here, the mortality seed, it compares that to the strike probability. Obviously, things that go down the fishway over the spillway don't have a strike. They may or may not pass based on some information you gave it on the route data tab. The other things will be highlighted in red, and the larger that bar, the higher that value for strike was, based in almost entirely on the strike calculations and the turbine geometry, which differs from turbine to turbine, as well as the fish length. Finally, it summarizes that up by simply saying strike, pass, no pass for a bypass, and then just uses a little color code here of kind of a visual cue of a check mark that it passed. X is a death, and the yellow button is a no pass, which you can quantify however you want. So to summarize, the model makes it really easy for any user, once you have the information on the units, to run through a simulation in a matter of minutes. And what I didn't show in that summary was you can run multiple simulations, change the inputs, archive those simulations, and do your own comparison, all in an Excel environment that I think most of us are familiar with. Certainly getting the turbine data is the hard part, but again, this is data that you will often find in a pad as part of relicensing or in other documents that are either readily available in the FERC environment or could be requested from a hydro company. I should point out that while, TBSA, there's nothing new about the method. This is one way to think about it, is this is a computer implementation of an existing method, that method being the Franke paper. That's very well accepted. Nevertheless, it's viewed as typically inferior to a field study. Third thing is the code has been thoroughly QC'd. So in ensuring that we did this correctly, Jessica in particular was particularly helpful in going through and then comparing the results from our model to some of the studies that we've pulled out of the FERC record for various sites, and we can reproduce those numbers. So we have high confidence this is doing what we claim it's doing. So, again, knock on wood, somebody down the line might find an error with it, but we haven't found one yet, or at least we've resolved all the ones we did find. So the model is available upon request. It's free. It's, as a free model, it's there's no warranty to it. Use at your own risk, of course. Sooner or later, we'll get it up on our website. But if you want it, simply email me or Jessica, and we can provide it for you. All right, folks, let me run you very quickly through one of the models. You'll see this is the kind of default name that we give it, turbine blade strike analysis. You'll notice the number there is the year, month, and day of the release. And the extension on there is your typical Excel extension, although you'll notice the XLSM indicates there's a macro or code embedded in it. Double click on that. Now when this opens, it will prompt you to enable the code. If you're not familiar with that, you should only do that on files that you're familiar with, and it's a file that my machine is familiar with, so it didn't even prompt me for that. When it does open, you'll notice a file name at the top. You can change that to whatever you like, but here are the three tabs that I mentioned before. This is the Methods tab. It gives all the good information about how this model was put together, ending with the glossary that I mentioned. Of note, in fact, if you're interested in the Franke paper, there's a hyperlink to it there that if you click on that, it will download the PDF for you right off the internet. The root data tab, of course, is where you want to spend most of your time. This is where you'll enter the information both about the turbines and any bypasses. Remember the general rule that anything in blue is user input. Now to get started, it may be a bit overwhelming of where do I get these numbers and what are the magnitudes of these kinds of numbers. So for your convenience, we've put a sample problem, an example problem in here. You just click on this button. It will say we're going to overwrite the data. Of course, there's nothing on there, and it brings in a bit of a contrived example where you can see both a Francis unit, a Kaplan unit, a propeller unit, a downstream fishway, and a spillway all in one project, and provides some probabilities of fish moving through each of those. Again, blue are things that you can alter, but it gives you an idea of what those values ought to look like, both for turbine diameters, for efficiencies, for turbine discharge amounts, and the RPMs, as well as the all-important lambda that I've mentioned a few times already. The last thing I'll mention here is that when you include bypasses, now bypass is anything that bypasses the turbine, that might be a fishway or a spillway, you can associate a mortality with it as well. Clearly a well-designed fish bypass should have a very low mortality, it's 2% in this example, but a very high spillway might have a high mortality. This one is 40%. So once all that information is included in the Route Data tab, you can move right over to the Simulation tab. And here you'll notice this looks just like the presentation with those buttons. There is a summary up here that is currently empty, and the first thing we need to do is tell it how many fish we're going to run through this example. So I'm going to run through 5,000 fish. Let's say, and this is again a bit contrived, but let's say particularly large fish, 24 inches in length, and I do this only to demonstrate the contrast with a smaller fish that we'll do later. Once we entered that in there, we're ready to run the model. We go over to the Run button, and depending on the number of fish, it may take a few seconds to run. Also depends on the speed of your computer, although I have a pretty inexpensive one. Didn't take too long, and now the entire sheet is populated, as I mentioned before, and this will run all the way down to hopefully 5,000 fish at the end. It does. And as I mentioned before, you can see each of the values, fish length, the route selection in here tells you where each of those fish went, the calculations on the strike probabilities, the all-important lambda, the mortality seed, which it compares to the strike probability to determine whether you've actually killed the fish, whether it passed, or what's labeled as a no pass, which is basically saying mortality through one of the bypass routes. And then all of these individual results in the last column are then summarized up at the top here. Last things, just real quick, you can archive those results. Now I've got a new sheet down here. This doesn't contain code in it. It contains the turbine data as well as the output that I can store for later use, change my inputs, rerun it, and each time I archive it, I can store any number of archived runs or simulations that I choose to. Finally, the last thing you can do is export the results to a separate sheet, and it prompts you for name here. You can see both a summary, and it will include sheets for every simulation that you ran. All right, that is rather quick, but that's how the model runs, and there's obviously a lot more to it. And if you have any questions, feel free to reach out to myself or to Jessica Pica. Thanks.